Good day and welcome back for the second part of our discussion on L'Hopital's rule. Let me give you the quick reminder of L'Hopital's rule. If we're evaluating a limit as x approaches a of f of x over g of x, and if this limit is one of our so-called indeterminate forms of type infinity over infinity or 0 over 0, that's simply saying when you break this function down into the top and the bottom individually, if the top is going to 0 and the bottom is going to 0, you would have an indeterminate form of type 0 over 0. If the top is going to plus or minus infinity and the bottom is going to plus or minus infinity, then you would have an indeterminate form of type infinity over infinity. In either of those cases, we can apply L'Hopital's rule to evaluate this limit. And the limit becomes the limit as x approaches a of f prime x over g prime x. And the idea is that by differentiating the top and the bottom individually, this will hopefully become a limit that we can evaluate more easily. Which is to say, we get it to the point where we can use our limit laws. So let me give you just a bit of intuition. So in this case of having, say, an indeterminate form of type 0 over 0, could I maybe give you an idea as to why L'Hopital's rule should be true? So starting with that right-hand side above, can I convince you that quantity is really the limit of f over g? So I'm going to just note in this case what we're really assuming is we have this indeterminate form of type 0 over 0. And furthermore, just so it makes sense to use L'Hopital's rule, g prime of a is not equal to 0. And if g prime of a is not equal to 0, it makes sense that this limit would simply be f prime a over g prime a. So it's not a 100% technically correct explanation, but just trying to give you some intuition. It's a property we will make frequent use of, so it's nice to be able to at least say it's reasonable to accept it as being true. I'll also mention, if you look in the textbook, you can find a more thorough explanation. Rewriting these, we can say f prime of a is the limit as x approaches a of the difference quotient, f of x minus f of a over x minus a. And g prime of a, our denominator, is also a derivative, which means by definition it's a limit of a difference quotient. And then if we go ahead and just simplify a bit, f prime of a we said is equal to 0, so we can cancel that off. G prime of a is also something we said is equal to 0. And what we would like to do is pull that limit out and just write it as a single limit. And when you write that quantity as a single limit, the top and the bottom both involve a 1 over x minus a, which we can cancel, and the only non-canceled terms that remain are the f of x and the g of x, which is precisely what we are hoping we would see. So in a very specific scenario, a little bit of intuition as to why we can expect L'Hopital's rule to be true. So let's now move on to an example. Let's evaluate the limit as x approaches 0 of tangent x minus x over x cubed. My intuition, as x approaches 0, remember tangent of 0 is 0, and x is going to 0. So the top is going to 0, the bottom is going to 0, which means we can apply L'Hopital's rule. And what I would like you to do is to pause the video, apply L'Hopital's rule, and I'll give you a hint. You're going to need to do a little bit of algebra at a certain point and apply L'Hopital's rule multiple times. So at this point, hopefully you've paused the video, you've put a bit of thought into this example. Typically in class, I would allow students somewhere between 5 or 7 minutes to work on it as I walked around and answered questions. So now L'Hopital's rule tells us the limit as x approaches 0, we take the derivative in the top, secant squared minus 1, and we divide by the derivative in the bottom. And recall from our previous discussion, each and every time you use L'Hopital's rule, you have to indicate that you have an indeterminate form and put a small LH over the equal sign. Now we have a new limit. If we can evaluate this limit, we're good to go. So it's kind of like just starting from scratch again. Now as x goes to 0, let me give you a quick reminder just so there's no confusion. Secant of x is 1 over cosine x, and cosine 0 is 1. So as x goes to 0, secant squared of x is going to 1. 1 minus 1 means the top is going to 0, and the bottom's going to 0 as well. So actually this is great. We have an opportunity to apply L'Hopital's rule a second time. And there's no limitation as to how many times we could apply it. Of course, we would like it to eventually end. So now when we differentiate the bottom, it would be 6x. And note, how many more times could we potentially apply L'Hopital's rule? If our denominator remains the same, it looks like one more time maximum, then we would be left with a 6 in the bottom. In the top, when we differentiate secant squared, we use the chain rule. So we take the derivative of the outside function, the 2 comes down, the new power is 1. We evaluate it at the inside function, secant, and then we multiply it by the derivative of that inside function, secant tangent. And just to kind of combine a few terms in the top, purely for fun, we can note that secant squared tangent, and the 2 in the top could make the 6 in the bottom a 3. And now as x goes to 0, secant squared of 0 is 1, but tangent of 0 is 0. So the top is going to 0, the bottom is going to 0. And this is probably way more fun than you were expecting, right? We now get a third and most likely final application of L'Hopital's rule. The reason I say most likely final is in the bottom we have a 3. When we differentiate the top, we need to use a product rule, but we've already differentiated secant squared, which requires a chain rule as well. So putting this together, we have the derivative of the first, and our work above suggests that the derivative of secant squared x is 2 secant squared x tangent times the second function plus the first function, secant squared, times the derivative of the second. And now, as x approaches 0, it looks a bit messy, but tangent goes to 0 at 0. So this first term in the top goes to 0, and we've already said secant squared x goes to 1. So this second term in the top goes to 1, the bottom goes to that constant 3. And in terms of limit laws, if we're going to 0 plus 1 over 3, that's simply a 1/3, and the value we've been attempting to find. As a reminder, when it comes to dealing with limits, in general, we do have to be a bit patient. Also, we need to be careful to organize our work in a single vertical column and use good mathematical notation. So not only are you indicating that you have these indeterminate forms when you use the L'Hopital's rule, but you're also writing an equal sign at each step and a limit at each step. And I am almost certain that whoever you had previously for Calculus 1 was probably fairly picky about such notational consistencies when it came to grading your work, and I will most likely be just as picky in this course. So be warned, always double check your work for good mathematical notation. Let's move on to now a slightly different example. And even though I say slightly different example, note it's still a limit. So let's just think about this kind of bigger picture intuition. As x approaches 0 from the right, what do x and natural log of x individually approach? Well, as x goes to 0, x goes to 0. If we want to picture the natural log of x, graphically, we have the curve in blue. And when you are substituting in a value of x close to 0 on the right, we see by inspection the function appears to be approaching minus infinity. So when it comes to evaluating limits, it's very useful to be able to visualize the common curves that we have encountered. Now, 0 times minus infinity. It turns out that this is also an indeterminate form. And because it's another indeterminate form, that indicates that 0 times plus or minus infinity is going to have no associated meaning to it. We can't just simply say, oh, it's 0, or oh, it's infinity. It turns out it could actually be anything. Now, unfortunately, I don't see any obvious algebraic manipulations that would help us evaluate this limit, but we do have this new limit law we've been discussing, L'Hopital's rule. So can we somehow relate it back to L'Hopital's rule? And the observation that I want to make is it's not a fraction, right? L'Hopital's rule is for these indeterminate forms of type 0 over 0 or infinity over infinity. But in either case, it's something over something. And a perfectly reasonable way to rewrite this is natural log of x divided by 1 over x. Because remember, dividing by a fraction is multiplying by its reciprocal. And let me make just a general observation that can be useful. So in general, if you have a function f of x times a function g of x, you can always write this as g of x divided by 1 over f of x. Or you could always write it as f of x divided by 1 over g of x. In this case, I decided to write it as ln of x over 1 over x because 1 over x seems a bit more palatable than 1 over the natural log of x. Now we can think about this equivalent limit. As x goes to 0 from the right, we've already noted that the natural log goes to minus infinity. Continuing on with our practice visualizing, 1 over x is this reciprocal function. So as we substitute in quantities close to 0 on the right, and we trace up, we see that 1 over x is going to be approaching positive infinity. That is to say, we have one of L'Hopital's indeterminate forms, infinity over infinity. So we can evaluate this limit by investigating the equivalent limit where we differentiate in the top and we differentiate in the bottom. And recall once again, dividing by a fraction is multiplying by its reciprocal, which is to say, we can simplify this by multiplying by x squared over x squared. And if you perform this algebraic simplification, what we end up with is the limit as x approaches 0 from the right. We do have a minus sign. We'll have an x in the top and a 1 in the bottom. And the limit as x approaches 0 of x is simply equal to 0. So we now have 3 different types of indeterminate forms. There's the first 0 over 0 or infinity over infinity. Then the newer indeterminate form is when we have a product that we're evaluating the limit of, and it's of this form 0 times infinity, or similarly, infinity times 0. In that case, you can rewrite that limiting function algebraically, resulting in an indeterminate form of type 0 over 0 or infinity, meaning that we can use L'Hopital's rule. We've completed the material associated with the first half of our section on L'Hopital's rule. So you are at a perfect position to go to the suggested problems, begin practicing, which we will also do in our upcoming video. So stay tuned and take care.